Okay.
Hello everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we have a really interesting hangout planned for you today. Astronomers using the Hubble Space Telescope have gone looking for water vapor. They've pointed the Hubble Space Telescope at 3 exoplanets, and in an attempt to try and find water on other planets beside our solar system. Now the good news is they found it. The bad news is they didn't find quite as much as they had hoped for. So we're going to be discussing some of these this discrepancy here a little bit later today. And with me, as they are every week, is Dr. Carol Christian from the Space Telescope Science Institute. She's the Hubble Outreach Scientist, and Scott Lewis from KnowTheCosmos.com, Virtual Star Party, all kinds of places on the internet. Welcome, Scott and Carol.
Hello.
Okay. So before I get to the introductions of our scientists today, I want to remind you that you can comment and interact with us by hopefully using the Q&A app on YouTube and G+. You can also leave comments on both of those places. We're also looking at Facebook and the Hubble Hangout hashtag on Twitter. So please ask questions, leave comments, and we will see them and talk about them here during the Hangout. So with me today are the astronomers who have been using the Hubble to make these measurements. But let me give you a little bit of foreground here, a little bit of background in the research they've been doing. They've looked at 3 hot Jupiter exoplanets. Now we'll talk about what hot Jupiters are in just a minute. And these stars are between about 60 and 900 light years away, and because, as the name hot Jupiter suggests, they are gaseous planets, and they're also very hot. They have temperatures between 1,500 and 4,000 degrees Fahrenheit. Now, before you get mad at me that I used Fahrenheit, I also did the conversion, and that is between about 800 and about 2,200 Celsius. But I know that's not good enough either for you guys, because you guys watch Hubble Hangouts to get real science information, and you want real units. So that's about 1,000 to 2,500 Kelvin. So these are hot, very hot planets, and they are orbiting more or less close to their stars than I think most planets are. But we'll talk about that here in just a little bit. So let's see who we've got here. I will start from, I guess I'll start with you, Peter. We have Dr. Peter McCullough. He is an astronomer at the Space Telescope Science Institute and member of the team who made these observations. Dr. Nicholas Cruzet, he's from the University of Toronto, an astronomer there. He used to be at the Institute. Now he's way far away. Hi, Nicholas.
Hi.
And also with me is Drake Deming, an astronomer. I didn't get your institution, but I'm sure
University of Maryland.
University of Maryland. Thank you. These are all members of the team. We also have I want to say his full name at least once. Dr. Niku Madhusudan, I think is right. Anyway, he wants you just to call him Madhu, and he is trying to join our hangout right now, but is having some technical difficulties. So we'll see how that plays out.
He is in India, so.
And he is. That's right. He is trying from India, where it is now tomorrow, I think. So. Yeah. Anyway, we'll be patient, and hopefully he can join us soon. Let's see. How about
from the future?
Yeah, he's from the voice from the future.
So, Drake, let me start with you. Can you give us an overview of what you were trying to do? I mean, it seems to me like I think Hubble astronomers are starting to get a little spoiled. It seems to me like the fact that you found water vapor at all is a really huge deal. But no, you didn't find enough. Now you're not happy that you didn't find enough water vapor. So tell us what you were trying to do.
Well, after hydrogen and helium, oxygen is the most abundant element in the cosmos. And so one of the most abundant molecules that you would form with oxygen is you would combine it with molecular hydrogen to form water vapor. So water vapor should be ubiquitous in all planets, even hot planets. We should find it in vapor form. Also, water vapor is a strong infrared absorber. So it has a band that lies within the bandpass of the Weve C3 instrument on Hubble. So we wanted to make a measurement basically.
So that's a good point. Water vapor is one of those things that prevents really good infrared observations from happening here on Earth. So you're right, it does.
Right, you can't see water vapor in exoplanets with ground-based observatories, at least not very easily at all, because the Earth's atmosphere has water vapor and it absorbs all the radiation from the exoplanet that wavelengths.
So, like I said, to me it seems like the really big news here is that you found water at all. I mean, is this the first measurement of water vapor in an exoplanet, or have we done it already somewhere else?
There were some measurements with Hubble using the NICMOS instrument, and those have been controversial because the noise in the NICMOS instrument is larger than it is with Weve C3. I think in retrospect, probably NICMOS was seeing water vapor, but it just wasn't as clear as it is now. With C3, it's really completely unequivocal. We see the shape, we see the characteristic shape of the band, we see the band head. Multiple groups observing the same planet get the same answer. It's now a very robust detection. However, the signatures we see are rather subtle. They should be stronger than they are, and that's the conclusion, that the planets are rather dry.
Okay, so you found them, but they are drier than you want them to be, and as you say, they should be. Water should be ubiquitous. Let's talk a little bit about these planets themselves. They, as I mentioned before, they are between about 60 and 900 light years away, and they're really hot. 800 to 2200 degrees Celsius. Peter, can you give us a little background on these planets and tell us what hot Jupiters are and how do they compare to other exoplanets that we know to exist?
Let's go back to 1995 when the first good detection with the radial velocity technique. This is looking for the stellar recoil velocity as a planet passes around it. And in 1995, the first detection of a planet of that sort was made. This is the planet 51 Pegasus B. And the surprising thing in that circumstance was that it was orbiting in just a few days. So its year, if you will, is not 365 days, but just 3 days. So that was quite unexpected. And that planet is called a hot Jupiter because it's Jupiter-sized, and it's very hot, as you've given the quantitative numbers for the temperature. I have a hard time appreciating those because I'm not a glass blower. I don't work with anything of that temperature, really. That's the way I think about it, is that if I was standing near that planet, I wouldn't want to be on it. If I was standing near it and looking at it, it would be kind of like an ember in a fire at night. I can just see it glowing kind of red there to my eye. Most of the emission is beyond where my eye can see. And I'm just picking up a little bit of the tail of that planet's emission, and I see it as a deep red. I guess actually a glass blower would have this experience much more often because their ovens are very, very hot.
So I used to be a firefighter, and so yeah, it gets pretty warm being that close to something that hot for a constant way. So yeah.
And that's a good analogy, actually. If you were on the surface of this planet and it's going around its star every 3 days, say, instead of every 365 days, it has to be a lot closer to that star. So that star appears 20 times bigger, like really big on its sky. And so imagine on a hot summer day how you can feel when you walk from the shade into the sun beating down on you. Well, now multiply that by 400 suns, and you get an idea for how hot it's got to be on the surface of these planets. Well, they don't have a surface, but in their upper atmosphere.
Wow. So so they compare. Well, I guess we can make a quick comparison. We call them hot Jupiters. Because they are much hotter than our own Jupiter by several hundred times. It sounds like. Is that correct?
Well, in temperature units, not hundreds of times, but the amount of light incident upon them by the star is 100 or more times that of Jupiter.
So are these are not, and then we talked about this a little bit in previous Hangouts, this distinction between these gas giant planets and brown dwarfs. These are definitely not brown dwarfs.
Well, it's hard to tell sometimes what something is. There's a definition. One definition is that the mass of the object is less than 13 times that of Jupiter, and then you call it a planet. If it's more than that, you call it a brown dwarf. But that's really a proxy for the fact that we're ignorant of how the planet formed or the brown dwarf formed. And in one circumstance of formation, you call it a brown dwarf. In another one, you call it a planet.
Okay.
But we don't know that, actually.
Right, and that's always a point of confusion from a lot of people. I always like to bring that up a little bit. I want to ask you guys to be patient while Madhu tries to connect from India. He's still having some difficulties, and so hopefully we'll be able to get him in here. I wanted to ask him a little bit about this particular finding, but let me turn this over to, let me ask Nicholas. Let me ask Nicholas Cruzet. You did a lot of the data analysis on these observations. What were you? What's your take on all of this? What were you? Were you surprised that these exoplanets were so dry as well?
So the first thing I was surprised of is to see how good were the data, really, because I've been working on NICMOS before, and now we are working on WIPC3, and the data are really, really good, and we can extract the spectrum of these planets quite easily, I would say, and we see the water right away. So there is really no doubt that we can see these signatures. So first of all, we are really pleased to see this water coming because we've been expecting that for several years now without clear detections, and now being able to see it right away was really, really a good surprise. Now the fact that it's lower abundance than we thought is actually very interesting, because we were relying on models so far without strong constraints on them to try to understand the formation of these planets. So it is the first very strong constraint on this water abundance, and from that it's really a huge step forward to understand how these planets formed.
Okay, so let's go back a little bit. You mentioned NICMOS. Tell us a little bit about that. What is NICMOS?
So NICMOS is still an instrument on Hubble Space Telescope. It was used to do spectroscopy up to 2008. At this point, it was not used anymore, and this was basically the first instrument to do this kind of measurements in this wavelength, together with another satellite, Spitzer. So the first measurements for this water vapor were done with NICMOS. But the instrument was not as good as WIPC3, and there was strong debates on how reliable were the detections.
So WIPC3. What is that? That's another camera on Hubble, right? What are its?
It's a new camera on Hubble.
NICMOS and WIPC3. I just want to give people a sense of what instruments we're talking about here.
So WIPC3, I don't know if we can say it this way, but it's the successor of NICMOS. Say, is that right to say, Peter? So we have NICMOS for the first.
The successor to NICMOS.
Yep. So it's better instrument, better data quality, and we get a better spectrum from that.
I have an analogy that I might add. I just had to turn in my 20-year-old Subaru, which was a wonderful car, and yet it had rusted out, and the guy basically said it wasn't safe to drive anymore. So we got rid of it. We got a brand new Chevy Volt, and that's the difference in driving experience between NICMOS and WIPC3. WIPC3 is a beautiful, wonderful new instrument, works great. And I apologize to Nicholas for making him work so hard on those NICMOS data. They were a real challenge to eke anything out of.
So NICMOS is an old Subaru. That's really kind of sad that you would put it that way. No, okay. So these 2008 was the last time NICMOS was. So these are old observations then.
Yes, and for several years we didn't have any ways to do these observations because NICMOS were not working anymore, and WIPC3 was not installed already. So we had this gap of several years with still this strong debate going on with no way to do further measurements. So having these measurements now is really a very good thing.
So just also for everybody's knowledge, WIPC, we're talking about WIPC3, that stands for Wide Field Camera 3. We just sort of pronounce it WIPC. So that's the there was a wide field camera too, which to me I thought this would be a successor to, but apparently it's NICMOS. So
well, I was speaking programmatically. You're right. The wide field planetary camera 2 was the predecessor to wide field camera 3, but the infrared capability on wide field camera 3 is a natural scientific successor to NICMOS. And I can extend my Subaru and Volt analogy a little bit more. The Subaru still runs. I was able to drive it in and trade it in, and maybe someday someone will use it again, just like NICMOS is still waiting for us to use it up in space. But just like the mechanic who said it's not safe to drive anymore, the scientific decision was made that NICMOS is not scientifically useful at this time, given the power of wide field camera 3's infrared channel.
Okay. Now, in the press release, there was a graph, or the results. You guys, Scott, would you mind? Do you have that handy for me? And then I will ask. I guess I'll ask Drake to comment on this. Can you see what Scott has up on his screen?
Oh, Drake has to unmute because we're getting a lot of noise. So, Drake, you need to unmute yourself by moving your mouse around and clicking it. Yeah.
Unmuted?
Excellent.
There you are.
Good.
So explain to us what we're looking. Can you explain to us what we're seeing here?
Well, I'll have to expand it a little bit before I can see it better. Okay. So what you're seeing here is spectra. So the horizontal axis of these graphs is wavelength in micrometers. So this is in the infrared, relatively near infrared. Over on the left part, beyond the edge of the graph on the left, would be optical light, visible light that your eye would see. So this is about a factor of 2 in wavelength, greater than optical light. And the y-axis of the graph is the amount of absorption that we see in the planet. So when there's a molecule absorbing, the graph will go, the line will go up. The blue points are the data. The red line is the model. It's a theoretical model of the atmosphere. It's what we should see for a given abundance of water. And I will point out, if those of you who are used to looking at astronomical spectra, most astronomers plot their spectra so that absorption goes down.
Right.
Exoplanet astronomers do it backwards. We plot it so absorption goes up.
Oh, good. Oh, good. I'm so happy they do it the opposite. That just makes it much better.
So up means more absorption, down means less absorption.
There is a reason for that. It's because
there's a reason, but we probably don't want us to go into that reason.
Okay, so we're not going to.
Just
so you know, there is
classified,
a reason. It's not just for fun.
All right. Well, at least
it's not classified.
Say there is a reason. So Scott is showing HD 189733B. There's also another one. If you can scroll up a little bit, Scott, it's HD 2094 58B. That one looks about the same to me than the other one.
No.
Where? Go back up. Go back up.
The difference between the not absorption and the strongest absorption is amazing.
Yeah,
sorry.
The 209 is the highest signal to noise.
Okay, so the numbers are a little different. And okay.
So I have a question, and one of the questions is, you were talking about hot Jupiters. You were talking about the fact, when we detect these, they have to be near the planet so that we can, near the stars so that we can even find them. And then you're doing this detailed analysis. So help us understand, since the planets are hot, why would you expect to see water at all?
So it's a very good question, and actually, being hot, these planets are better targets to identify water vapor. So again, I'm repeating that, it's water vapor. So to be able to be seen, the water has to be in form of vapor, and the hotter your planet, the more vapor you have, and the hotter in the atmosphere it would be. So if I take another example, for Jupiter itself, in our solar system, this planet is very cold. It's not a hot Jupiter. It's like a cold Jupiter. So it's cold, and the water is very deep in the atmosphere. Now, going to hot Jupiters, they are much hotter, so the water is upper in the atmosphere, and then it's easier to detect. So actually, hot Jupiters are better targets than Jupiter itself to detect this water vapor.
Because the water vapor then is not sinking down, but it's actually up in the higher part, and so you have to accommodate that in your model as well. So it's the mount and what layer it's in.
Yes.
Ah, okay.
Okay, this is a question I would ordinarily ask Madhu, but he's not here, so I guess either Peter or Nicholas, whichever one feels comfortable, because we just lost Drake again. Why these why these systems? Any particular reason?
So there is one reason, is that these three systems were the first observed with WC3 for the spectra, or the first hot Jupiter observed with WC3. So the first measurements, basically. And the second reason is they span a wide range of temperature, from one being a rather cool hot Jupiter, so still much hotter than Jupiter, but on the coolest end of what we call hot Jupiters, and one kind of in the middle, and another one which is a really, really hot Jupiter. So by spanning these three, yes, super hot Jupiters.
Really, really hot.
Yeah, so by doing that, we find a whole range of temperatures for these planets, and this kind of gives us stronger constraints that's spanning only one kind of planet. And
so you pick these?
Yeah,
and because they were representative of hot Jupiters, a range.
Yes, and for the three of them, we find a much lower water abundance than what we expected. So it seems to be something maybe common for Jupiters, but at least it spans the whole range of temperatures. So all these three planets have the same low water vapor abundance.
I can add to what Nicholas said, and I agreed with everything what he said. I'll just add that these planets orbit stars that are very nearby, relatively speaking, therefore very bright. The brightness of the star is helpful to us in improving the sensitivity. We could make these observations if the stars were, say, 100 times fainter. We just wouldn't have enough photons, particles of light, to count up to make these measurements.
Okay, good. Thank you for adding that. So you guys looked at these things for water vapor, and I'm glad that Nicholas is calling it. I keep saying water because that's a little sensationalistic, but what we're really talking about here is water vapor.
Yes, water in the form of vapor. Yes, gaseous water.
That's right. And so you found some, but not as much as you thought. How much less? I mean, what were you expecting? And I'll go with, let's see. Is Madhu here?
I see his picture.
Are you there, Madhu?
Yeah, I just joined in.
Awesome. Can you hear me okay?
Can you hear me?
Yes.
Yes.
Good. All right. Well, now that you're
here. Okay, great. So finally this seems to be working.
Good. All right. Yeah, we seem to hear you just fine. So let me just we've talked about a lot of things, and but I just want to jump in with a question from you. You were looking at these three exoplanets. For water vapor. You didn't find as much as you thought. How much less did you find versus what you expected?
So it depends on what assumptions you make about planet formation, but it's less by a factor of 10 to 1,000 than what we had expected.
A factor of what? I'm sorry.
10 to 1,000?
Yeah, between a factor of 10 and 1,000.
Between a factor of 10 and 1,000?
Yeah.
Oh, okay. That's a lot. That could be a lot less. Then. Okay.
Yeah. So a lot of it depends on what your assumptions about planet formation are, how much planetesimals the planet had accreted when it formed. Yes. But according to the standard core accretion theory, and if you use Jupiter, for example, in the solar system, there's a prediction that Jupiter should have about a factor of 7 higher oxygen abundance than water. The oxygen to hydrogen ratio in Jupiter's atmosphere should be a factor of 7 higher than the oxygen to hydrogen ratio in the Sun. If you made that same assumption for all hot Jupiters, for example, the abundances, the water abundances we are seeing are anywhere between a factor of 10,000 across the board, across the three hot Jupiters that we had looking into.
Oh, that must have, yeah, that is quite a bit less. No wonder everybody was disappointed. Okay, well, so Drake has already given us a good background into why we would expect to see water on so many places and so much of it. But in the press release, it was mentioned that because this is less than what we thought we would find, or what you thought you would find, this kind of does a little bit of damage to some of the current theories of planet formation. What theories are being challenged here by this finding, by this observation?
Well, I mean, the basic challenge is that water is, based on our theories of how these planetesimals form, oxygen is the most dominant element in all these planetesimals, be it in rock phase, in the silicates, or in water ice. And when you form a planet, a giant planet, according to the co-accretion model, you basically accrete a lot of these planetesimals and enhance all the elemental abundances in the planet. We see that in Jupiter. We know that many of the elemental abundances are enhanced in Jupiter's atmosphere, like carbon, nitrogen, sulfur, and so forth. But we don't know the oxygen abundance in Jupiter's atmosphere. So we only have theoretical predictions for the oxygen abundance in Jupiter. Right? And those predictions consistently show an overabundance of oxygen in Jupiter. If we make the same extrapolation for hot Jupiters, we just don't see the amount of water that's predicted. So that's the basic challenge.
Okay, so the core collapse model that a lot of people use to...
No, core accretion.
I'm sorry, core accretion model that people use to describe the formation of these gas giants is not exactly matching up with what people are seeing. Is that what you're saying?
In hot Jupiters, yes.
Yeah, in hot Jupiters. Okay. All right. So.
So I have a question then. So is that what you're saying is that there's less oxygen distributed through this exoplanet system? It isn't the same as what was in our solar system? And I had a second question, which is that we hear sometimes that there is material that comes in from the outer part of the solar system and deposits water on the inner part of our solar system. So my second question is that not happening, or there's just less water in that whole system, or we don't know, or whatever?
Well, the short answer is we don't know, and it's not just for hot Jupiters. It's not just for hot Jupiters. Even in our own solar system, we don't know the oxygen abundance. So there's a probe called Juno, which is a satellite going to Jupiter. It'll reach there in about a couple of years' time now. In 2016 is the tentative date when it'll reach there. And that's expected to find the oxygen abundance on Jupiter. Okay, so today, as of today, we don't even know the oxygen abundance in the giant planets in our own solar system.
Wow, that's
interesting. So we are using Jupiters as a metric to test some of our predictions for Jupiter in the solar system. So that's the state we are at. Now, whenever we are saying that we are seeing less water than is expected, we are saying less water than is expected for even Jupiter in our solar system, but even for that, we don't know the exact answer yet.
Okay, so does this have any implications for other planets besides hot Jupiters? I mean, what about smaller, more rocky planets like the Earth or Earth-sized planets? Does this have any implications for the abundance of water vapor on those?
It's hard to tell because giant planets are formed in a fundamentally different way than rocky planets in our own solar system, and we expect the same in other solar systems as well. So it's hard to tell how the water has been distributed, and there are so many channels of forming giant planets by co-accretion or gravitational instability and how the planets migrated and so forth. There are so many uncertainties in the whole process that today I don't think anyone actually knows how hot Jupiters got to where they are, very close to their orbits. So it might be that there is plenty of water in the system, but then the migration formation pathway could be just unique, that it doesn't accrete a lot of that water. Okay, so that could be one path. We just don't know is the short answer.
Well, but it sounds like we're getting off to a pretty good start and getting some of these estimates down a little more accurately. In the press release, you said that this was one of the most accurate measurements of water vapor done so far. Is that correct?
Right.
Okay, so you're pretty certain about the abundances and the fact that it's there. So that's good news. Peter, I want to go to you real quick. Scott, I had Scott bring us a exoplanet distribution graphic. We're talking about hot Jupiters, obviously. That's one kind of exoplanet. But can you give us what sort of a big picture discussion or idea of what other exoplanets are out there, and how does this compare with the numbers of other planets that we see in the universe when we look?
Well, hot Jupiters are rare. In a sense, we know that because no such object exists in our solar system, but that would be jumping to a conclusion just based on the fact that here we are and it's just one example. But the graph you're showing, the sizes of planet candidates, this comes from Kepler up in the upper left-hand corner. We know statistically that more than 90% of these candidates are indeed planets. We just don't know which ones are which. But in a statistical sense, we can trust this graph. And it shows for stars like the Sun, but not the Sun, you have this distribution of planets that have been detected by the Kepler satellite. And there will be a tendency to miss the very smallest planets. So things smaller than the Earth are probably underrepresented in this graph compared to reality. This is just what we can see, and we're likely to miss the small ones. And then in the super-Earth size, that's an interesting new contribution to humanity's understanding of the cosmos, in the sense that in our own solar system we have no planets in this range. There's a desert, if you will, in the distribution between the terrestrial-sized planets and the gas giant planets in our own solar system. But in other solar systems we see these super-Earths, and you can see they outnumber the Earth-sized planets about 2 to 1. And then the Neptune-sized ones we have even more, according to this graph. And then look at the Jupiter-sized ones, and then even larger ones. Those are down by a large fraction compared to the Neptune-sized ones. And the number that are truly hot have periods less than a week, say. That's going to be an even smaller fraction of those bars that are colored red in the diagram. So hot Jupiters are pretty rare, but they are easier to see. And I remember speaking with Jeff Marcy, one of the more famous planet hunters in the United States. He lives out in California, where I got my PhD degree. He and I used to play volleyball together, and I told him, you know, Jeff, someday people are going to find these planets, but they're going to find them much like the drunk who looks for his keys underneath the streetlight. And you ask him, why are you looking for your keys underneath the streetlight? And he says, well, I lost them over there in the dark, but I can't see them in the dark, so I'm looking over here where I can see. So we're doing that largely for the hot Jupiters. They're easy to see, so they were the first to be found and the first to be studied.
And I can confirm that in LA that happens all the time. So I see that.
So you started this by saying that our solar system is not typical of this distribution, then. So we don't have these characteristics.
Well, we don't have any of these super Earth-sized planets in our solar system, and whether that's just luck of the draw or whether it has a deeper meaning, I'm not the one to say.
Sure. Okay, well, I have a couple of questions here. Here's one from Hugo Burnham. He's always asking good questions, and his apparently is $6,400. The $6,400 question, though, what does the lack of H2O mean for the formation of these 3 exoplanets / ultra dark brown dwarfs? And we've touched on this briefly, but do you want to add anything more to that?
I think Madhu is really the one to take the $6,400 on that.
Okay.
Yeah, Madhu, tell us.
Did you hear the question, Madhu?
So, yes. So, I mean, the maximum we can say at this point is that they're only giving us some clues as to how these planets might have formed or migrated, but no confirmed answers yet. We can only say at this point. So, first of all, one has to be clear that there are other hypotheses which are being played around for the explanation of low water abundances on these planets. Maybe there are clouds or hazes or something, and which are blocking the atmosphere, and we are just seeing the part of the atmosphere that is not blocked. So there is that hypothesis as well. There are some problems with that hypothesis, but the bottom line is that if the low abundances we are seeing is really the representative of the bulk H2O abundance of the planet's atmosphere, then it's actually telling us something very serious. It's telling us that you need to accrete a lot less water than you would in a normal core accretion formation process. Okay, so how these planets have formed, they have to escape a whole sequence in their formation process of just accreting water-rich planetesimals. It could be that, I'm just hypothesizing here, and we have done this in the paper as well, it could be linked to the planet's formation, that it formed in an area, in a region of the disk which is inherently water poor, and there have been theories suggesting such scenarios, or the planet migrated in a way that it escapes this accretion of water-rich planetesimals in its movement from wherever it formed in the disk to its current location very close to the star. Okay. So what exactly is causing the end abundances we are seeing? We don't have enough information nor a conclusive theory yet. But all we can say is that something is happening in either in the formation or in the migration process of this whole of the whole evolution of the hot Jupiter, which is escaping this accretion of water-rich planetesimals, and that's a fundamental insight into understanding this thing.
My naive view of this whole thing is that it would seem to me like areas close to the star would be water poor, but maybe, and this might be a selection effect of just having planets close to the star. It would seem to me like that would kind of make sense, that you would find maybe less water in a planet that formed closer to a star than you would farther away. But then that's, like I said, that's my naive view. Do you have a sense of a hunch about if this is common or not? These among hot Jupiters, this lower amount of water vapor.
So you bring about a good point, actually, that if regions in the disk closer to the star would have lower water vapor because they're just hotter.
Right.
But the catch is, even if you form the planet in such regions of a disk, then you would end up with having a solar abundance or a stellar abundance of oxygen to hydrogen ratio in the planet. Okay, you cannot go below that, and the abundances we are seeing are even below solar abundances.
Okay, well, I'd love to get into solar abundances. Is that something is that a pretty simple thing for you? Can you put that into some layman terms for us, or is that a really, really hard concept? Because I know what you're saying. Compared to even the solar abundance of the star, it's low. So,
right. So it's not a very hard concept. It's just I think Drake mentioned this point before. Oxygen is the third most abundant element in the cosmos, and it's the same for most stars as well. In the sun, for example, after hydrogen and helium, oxygen is the most abundant element. And what that really means is that if you took the oxygen to hydrogen ratio by number, that comes to about 500 parts per million. Okay, so that's what one means by solar abundance oxygen. Is the oxygen to hydrogen ratio is about 500 parts per million.
Okay, all right, good. Thank you. Well, thank you, Hugo. That was a good question. You'll have to see the lady on the way out for your $6,400. Go ahead, Carol.
I have a question. So anyone on the panel, so you have less water in the hot Jupiter in these three systems. And you're bringing up solar abundance. So what do you know about the abundance of the parent star compared to the abundance of the sun? I mean, I'm thinking, if it's lower, if the parent star is lower, then the planets would be lower. But if they're like the same, then you would go, what's up with that?
Right, Carol, that's a good question. I don't remember the numbers. We probably had them in the papers, the original papers. But the abundances, as I recall, are not that different from the sun.
They're not shocking.
Certainly not factors of 1,000, nothing like that.
Okay, yeah. Okay.
Maybe a factor of 2.
Yeah, they're in the vicinity of a factor of a few.
Okay, I have one from George Lloyd from the YouTube. He asked this a few days ago, or left a comment a few days ago, and he says, now that Gliese 581d and G are potential exoplanets in that their existence is now being disputed, how accurate is this data for the 3 stars that we have here? How accurate are you guys? Can you give us some sense of this, and maybe, I don't know, percentage terms, perhaps?
I think we can say
how about Nicholas? Perfect.
5 sigma detection easily, so it's what we call very accurate.
Okay. So you're very confident about this discovery.
Yes, because we have several measurements with several teams doing the work with several data analysis algorithm. We've been trying to do that before, and it didn't work. Now we really see that it's very clear.
So you'd be willing to bet the $6,400 of Madhu's money on this, and be like, no, it's cool, we got it.
Yeah.
I'll bet any amount of Madhu's money. How about that?
I should point out something here. Okay. The Gliese planets that disappeared, that's based on radial velocity data. For these giant planets, the measurements are entirely different. It's an entirely different kind of analysis, an entirely different kind of measurement. These planets are certainly not going to disappear, and indeed our water detections are not going to disappear. This is a completely different kind of measurement.
Okay.
Yeah, I agree with that. I can add, though, that the precision of the measurement, I agree with Nicola, that it's a very secure measurement in the space that was shown in a graph earlier, where you had points moving across in wavelength. And you saw this characteristic bump at the 1.4 micron wavelength at which we know water vapor absorbs. That's very secure. What's less secure is the ratio or the abundance of water in the atmosphere. And in fact, the measurement of that is stated in the papers and was said earlier. It's a little bit less than solar, all the way down to, I think it was 1,000 times less. So there's a very broad range that's consistent with the data, and this is not a problem with the measurement so much as the technique itself is insensitive to differences in the abundance. So very small abundances have almost the same effect as larger abundances on this graph. So we can see very weak spectral lines almost as well as we can see very strong spectral lines. So we can measure only accurately in, if I can use this term, the logarithm, rather than in the quantity itself.
Nice. Okay. So thank you. That was a good question. I just want to report to our regular YouTube viewers that a very sad thing, that Petaflux, who is usually first, is in fact fourth today. Just thought I'd point that out. Yeah. So, okay, Patrick Festa from YouTube is going, for any planet hunter, this for any of you, do you have a list of stars/planets that you would like to study this way in the near future, or is that wish list still being compiled? This is a great question for what I was going to ask you, which is what's next for you guys. So, who wants to take that? Madhu?
Yeah, I can take that. We constantly write proposals after proposals for HST time and other ground-based telescope and Spitzer time with this kind of a wish list. So we do have, or I do have a list of names I can suggest for hot Jupiters, and they're already being observed right now as we speak. So unless you want me to spell those planets, I would just limit it to say that there is a long list.
Long list, and back to hot Jupiters again, right? To sort of get more statistics.
Yeah, I mean, it's without question that today, with current state-of-the-art technology, hot Jupiters are the best candidates for water measurements until JWST comes along. That's not questionable at all. It's the real question is which hot Jupiters are the best candidates to study, and a lot of factors go into planning these observations. So good.
So that brings up another point. Peter mentioned in the earlier that one of the reasons you're looking at hot Jupiters is that they are the easiest to see. You look there whether your keys are there or not because you can see there. JWST, since you brought it up, ought to be able to improve this a little bit. Can somebody? How about you, Peter? Give us a sense of what might be open with JWST that currently isn't with Hubble as far as this research.
I'd be happy to do so, and I'm sure any one of my colleagues would do a good job on answering this question. But since you deferred to me, I'll just point out that while we were on this call, I got an email, and I snuck over and read it a little bit. This is from a colleague, Warren Beneke at Caltech, and we are planning new observations with Hubble, and in answer to the question of what planets might we be observing next, they come by these phone numbers. One is HD 97658.
I know, I love those.
With Hubble. The other one is 55 Cancri E, and there's two more that we're doing. They all have the characteristic of being much smaller than the planets that we're talking about today, the hot Jupiters. These are more like the super-Earths that we've been talking about as not seeing any examples in our own solar system. So yes, we're planning to do those sorts of observations, and the Time Allocation Committee awarded us a few days of Hubble time to study these objects.
Okay.
What would James Webb do? Well, James Webb is also going to be a very competitively awarded time, and whatever programs are deemed the most scientifically interesting at the 2017-2018 time frame. Those are the programs that James Webb is going to do. I would be very surprised if they don't come back to these very same planets and just do a bang-up job measuring the spectrum all in one go from about 1 micron all the way out to 5 or even 25 microns and see with clear, the difference between me wearing glasses and not, basically. There was a time in my life when I kept putting it off, and I would go, why do these exits always show up so quickly? Why do they not make the signs bigger? And why can't I see? Well, finally, when I got a pair of glasses, I said, oh, now I can figure this out. And that's what we're going to do with James Webb. We're going to figure this out. It's going to be quite clear with the glasses of James Webb.
Awesome. Excellent answer. Okay, here's one from Adam Synergy. He's asking, this is from the Q&A app. How do these results, the ones you have here today in the press release, compare with the lack of water the Galileo spacecraft observed when it dropped into Jupiter's atmosphere? Drake, can you comment on that, or
I can
get you back into this?
I think Madhu's probably chomping at the bit to say something. But let me just comment that the Galileo probe entered a dry spot. It's believed it entered a dry spot on Jupiter. So its actual measurements may not be so relevant to the global abundance of water on Jupiter. And after that comment, I'll turn it over to Madhu, and he can elaborate.
Okay, go ahead, Madhu.
It's interesting that it's actually harder to measure water vapor in Jupiter's atmosphere than it is on hot Jupiters, for this very simple reason that Jupiter is just way, way cooler than even the water condensation curve. The hottest temperatures, above the 1 bar pressure level, which is pressure lower than 1 bar, are less than 200 Kelvin. Okay, so all the water is expected to condense out to very low depths in Jupiter's atmosphere. So if you're not finding water in if the Galileo probe did not find plenty of water in Jupiter's atmosphere, one simple explanation is that it didn't go deep enough that the water was abundant in its actual, where you could see the actual abundance of water. So the probe failed too early. And as Drake mentioned, another widely accepted explanation is that the probe fell on a hot spot, on a dry spot in Jupiter's atmosphere, which means even at the pressures the probe probed, the water was less than normal.
Okay, so I get because Jupiter is so much cooler, the water vapor that would be there would have been a lot lower in the atmosphere, and you're saying that it's possible that one explanation could be that it just didn't go down far enough. The probe didn't make it down far enough to detect anything.
That is the favored explanation. That is the commonly accepted explanation.
Good. Good.
But the Galileo probe,
probe went down far enough; it just wasn't able to send out information at that point. I suspect the probe is well down into the bottom of Jupiter by now.
Okay.
Right.
Good question. Thank you. So
Right.
Hans Milling is speculating perhaps the missing water has been blown off the planet, just like Mars. The solar winds must be much stronger when it is that close to the parent star, and the water is not liquid due to the heat. We touched on some of this earlier, but even with the geometry of the orbits and things like that, and the sizes of the stars versus the planets and things, even with all of those things taken into account, they're saying that they still are not getting, it's still not adding up to enough, or as much as it should have. So, but good comment. And Nastya Kuchanova is asking, could Hubble be the most mighty telescope again? And I'm like, was it ever not the most mighty telescope ever? Of course it's the most mighty telescope.
Absolutely.
Yeah, it can definitely be the most mighty telescope again. I don't think it ever was dethroned, but just to be sure, I now pronounce it mighty.
And Carol's
Okay.
got to go because she's baking in Phoenix and she's got to run to the airport. So bye, Carol. Thank you.
Bye, Carol. Thank you
Bye.
very much. We
Thanks.
will see
Thanks,
you
guys.
next.
All right.
We will see you next week.
Okay, thanks. Bye.
All right. Okay, so so we talked a little bit about where you guys are heading next. Do you have any more Hubble observations planned? Can we check back in with you anytime in the next year or so to see how things are going?
Yes,
That would
sure.
be delightful.
Okay. All right. Well, I guess we'll go ahead. Wait a minute. Let me check with Scott first. Am I missing anything, Scott? Did you see anything on Twitter, or any questions, comments there?
Everything on Twitter is pretty good. You know, a lot of sharing out and retweets. So you guys are awesome.
Yeah. Thank you guys very much.
I'm seeing one here from Patrick Calhoun on the Q&A app, and asking about observations as far as, you know, can I see a hot Jupiter with an 8-inch from Earth, and if so, does it look just like a star? And so what you know, these hot Jupiters are so close to their host star anyway that, you know, we're observing either, you know, transit or the radial velocity, so you're not going to be able to actually observe it that way that we can do here on Earth with an amateur telescope.
If I can jump in, actually, there is an opportunity for astronomers with very small ground-based telescopes to detect these objects. When the planet passes in front of the star, the silhouette of the planet blocks about 1% of the light from the star. And this is measurable with small instruments by people that spend a lot of time and effort to develop their technique to an expert level. That's in fact how we discover many of these hot Jupiters, is specifically by doing that sort of observation. And once you know when to look and where to look, it's not impractical for a person in their own backyard to see the effect of the planet passing in front of the star. Now, they wouldn't be able to measure the spectrum as we've done here with Hubble, but they can see the overall effect of the planet passing in front of the star.
Right. So we'd be able to see the, you know, the luminosity dip down a little bit. I did a hangout about 2 years ago. We did a direct observation of a transiting exoplanet in a hangout. So we're observing it, and we're getting the data from it, because we're not actually really seeing much when we're looking at that star. But when you're able to go through and compile the data afterwards, you're able to graph it down. You are able to see the dip as it transits across. So that was
see it with
from
your eye.
right. You're not
You don't
going to be
see it with
seeing
your
it with your
eye.
eyeball.
Numbers on a graph.
Yep. And so later we're like, oh, well, here's this light curve. This is what we were seeing, and that's, you know, that's a big part of how we detect anyway, especially with the transit method. Is we're looking for those dips of light over time as it crosses between our field of view and that star.
Very good. Good catch. I'm glad you got that one in, Scott. Thank you. So there, I just need to scroll a little bit more, and then Steve Harvey again with how certain can you be of these measurements of water? We just talked about that. Can you rule out other bodies in space between the Earth and the star? For example, dark nebulae or even comets, giving you false readings from their spectrum instead of the exoplanets. So, so we've already talked about how certain we are of these measurements. But what about that? Is there anything? How can we be sure that there's nothing in the way?
We can rule that out. We can rule that out because the measurements are phased to the orbit of the planet. We see the water come and go when the planet passes in front of the star.
And we would not see that if there was something intervening in the way. We would see some disconnect. Oh, okay, good. Awesome, thank you. Okay, folks, I guess we'll stop there. I don't think I see any other questions. Is this a video presentation? No, it's live. Not it's not recorded. So hey, I want to thank everybody for joining us. I want to thank all of the people and Nicholas, Drake, Machu, and Peter for joining us. Thank you very much for spending time. And on behalf of Scott Lewis and Carol Christian, who had to leave early, I want to thank you guys for watching. Next week we have another hangout. Apparently there is a calibration workshop going on at the Institute, and we're going to talk about calibrating Hubble Space Telescope data. So we'll have people from the Institute talking about how we take data from the telescope and turn it into science. So,
and then we'll have a 2-week hiatus.
And then after that, we'll take 2 weeks. That's right. We're going to be woohoo!
So catch it up now and store it all in, and then we'll be back with more amazing Hubble Hangouts for you guys.
That's right. So thank you all for watching, and as always, keep looking up.
Thank you.
Bye, everyone.
Who have been using the Hubble to make these measurements. But let me give you a little bit of foreground here, a little bit of background in the research they've been doing. They've looked at 3 hot Jupiter exoplanets. Now we'll talk about what hot Jupiters are in just a minute. And these stars are between about 60 and 900 light years away, and because, as the name hot Jupiter suggests, they are gaseous planets, and they're also very hot. They have temperatures between 1,500 and 4,000 degrees Fahrenheit. Now, before you get mad at me that I used Fahrenheit, I also did the conversion, and that is between about 800 and about 2,200 Celsius. But I know that's not good enough either for you guys, because you guys watch Hubble Hangouts to get real science information, and you want real units. So that's about 1,000 to 2,500 Kelvin. So these are hot, very hot planets, and they are orbiting more or less close to their stars than I think most planets are. But we'll talk about that here in just a little bit. So let's see who we've got here. I will start from, I guess I'll start with you, Peter. We have Dr. Peter McCullough. He is an astronomer at the Space Telescope Science Institute and member of the team who made these observations. Dr. Nicholas Cruzet. He's from the University of Toronto, an astronomer there. He used to be at the Institute. Now he's way far.
Oxygen is you would combine it with molecular hydrogen to form water vapor. So water vapor should be ubiquitous in all planets, even hot planets. We should find it in vapor form. Also, water vapor is a strong infrared absorber. So it has a band that lies within the bandpass of the Weve C3 instrument on Hubble. So we wanted to make a measurement, basically.
That's a good point. Water vapor is one of those things that prevents really good infrared observations from happening here on Earth. So you're right, it does.
Right, you can't see water vapor in exoplanets with ground-based observatories, at least not very easily at all, because the Earth's atmosphere has water vapor and it absorbs all the radiation from the exoplanet at the wavelengths.
So, like I said, to me it seems like the really big news here is that you found water at all. I mean, is this the first measurement of water vapor in an exoplanet, or have we done it already somewhere else?
There were some measurements with Hubble using the NICMOS instrument. And those have been controversial because the noise in the NICMOS instrument is larger than it is with C3. I think in retrospect, probably NICMOS was seeing water vapor, but it just wasn't as clear as it is now. With C3, it's really completely unequivocal. We see the shape, we see the characteristic shape of the band, we see the band head. Multiple groups observing the same planet get the same answer. It's now a very robust detection. However, the signatures we see are rather
far away. Hi, Nicholas.
Hi.
And also with me is Drake Deming, an astronomer. I didn't get your institution, but I'm sure
University of Maryland.
University of Maryland. Thank you. These are all members of the team. We also have I want to say his full name at least once. Dr. Niku Madhusudan, I think, is right. Anyway, he wants you just to call him Madhu, and he is trying to join our hangout right now, but is having some technical difficulties, so we'll see how that plays out.
He is in India, so.
And he is, that's right, he is trying from India, where it is now tomorrow, I think. So. Yeah. Anyway, we'll be patient, and hopefully he can join us soon. Let's see. How about
from the future?
Yeah, he's from the voice from the future.
So, Drake, let me start with you. Can you give us an overview of what you were trying to do? I mean, it seems to me like I think Hubble astronomers are starting to get a little spoiled. It seems to me like the fact that you found water vapor at all is a really huge deal. But no, you didn't find enough. Now you're not happy that you didn't find enough water vapor. So tell us what you were trying to do.
Well, after hydrogen and helium, oxygen is the most abundant element in the cosmos. And so one of the most abundant molecules that you would form with a subtle, it should be stronger than they are. And that's the conclusion, that the planets are rather dry.
Okay, so you found them, but they are drier than you want them to be, and as you say, they should be. Water should be ubiquitous. Let's talk a little bit about these planets themselves. They, as I mentioned before, they are between about 60 and 900 light years away, and they're really hot. 800 to 2200 degrees Celsius. Peter, can you give us a little background on these planets, and tell us what hot Jupiters are, and how do they compare to other exoplanets that we know to exist?
Let's go back to 1995, when the first good detection with the radio velocity technique. This is looking for the stellar recoil velocity as a planet passes around it. And in 1995, the first detection of a planet of that sort was made. This is the planet 51 Pegasus B. And the surprising thing in that circumstance was that it was orbiting in just a few days. So its year, if you will, is not 365 days, but just 3 days. So that was quite unexpected. And that planet is called a hot Jupiter because it's Jupiter-sized, and it's very hot, as you've given the quantitative numbers for the temperature. I have a hard time appreciating those because I'm not a glass blower. I don't work with anything of that temperature.
Okay.
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we have a really interesting hangout planned for you today. Astronomers using the Hubble Space Telescope have gone looking for water vapor. They've pointed the Hubble Space Telescope at 3 exoplanets, and in an attempt to try and find water on other planets beside our solar system. Now, the good news is they found it. The bad news is they didn't find quite as much as they had hoped for. So we're going to be discussing some of these this discrepancy here a little bit later today. And with me, as they are every week, is Dr. Carol Christian from the Space Telescope Science Institute. She's the Hubble Outreach Scientist, and Scott Lewis from KnowTheCosmos.com, Virtual Star Party, all kinds of places on the internet. Welcome, Scott and Carol.
Hello.
Okay. So before I get to the introductions of our scientists today, I want to remind you that you can comment and interact with us by hopefully using the Q&A app on YouTube and G+. You can also leave comments on both of those places. We're also looking at Facebook and the Hubble Hangout hashtag on Twitter. So please ask questions, leave comments, and we will see them and talk about them here during the Hangout. So with me today are the astronomers